This video is supported by the National Science Foundation.
Hello, I'm Olivia, and I am a member of the Florida Institute for National Security at the University of Florida. I'm here to continue presenting a tutorial on reverse engineering integrated circuits from scanning electron microscope images using artificial intelligence for hardware assurance. This video is part 3 of this module, so if you haven't already seen parts 1 and 2, you should probably do that. The link for parts 1 and 2 are in the description, so go watch them if you haven't already. The objectives for this module have remained the same. We will be using artificial intelligence to complete a project on hardware reverse engineering. The lectures are tutorial style, so you can follow along and build your own project as a resume booster and/or professional development. Last time, we went over several topics in image processing and computer vision and applied them to our project. Specifically, we did mean filtering for pre-processing, Otsu thresholding for segmentation, and binary morphological operations for post-processing. In this lecture, we will be introducing some topics in unsupervised machine learning and applying them to our code pipeline for the project. Again, this video assumes you've already watched parts 1 and 2, so if you did not, please refer to the prerequisites in the description. And like last time, this tutorial is best if you follow along with me, so feel free to pause, rewind, or slow down this video at any point and refer to the documentation whenever a new method is introduced. Machine learning, or ML for short, is a subset of artificial intelligence that involves algorithms that automatically learn patterns from data. There are a couple different types of machine learning. Unsupervised learning can learn in the absence of labeled data, so in our case, the ground truth image. This is kind of like when you're studying for an exam and are given practice problems but no solutions and are told to just figure it out. Supervised learning learns directly from labeled examples, so in our case, the ground truth image. This is kind of like when you're studying for an exam and are given practice problems with solutions that you can just use to study for the exam. There are other types of machine learning, such as reinforcement learning, also known as trial and error learning, or semi-supervised learning, which is a mix of supervised and unsupervised learning. But for this module, we are mostly focused on the first two, unsupervised learning in this lecture and supervised learning in the next. In short, unsupervised learning learns without ground truth, and supervised learning learns from ground truth. Machine learning is a subset of artificial intelligence and can overlap with computer vision and/or image processing, but doesn't necessarily need to. For more information, please refer to the Pattern Recognition and Machine Learning book by Bishop cited in the description under Additional Resources. A typical machine learning segmentation pipeline might look like this. An input image is taken and features are extracted using image processing, computer vision, and/or some other method, segmented using machine learning, then post-processed using image processing. The final result is then evaluated, and the rest is similar to the image processing, computer vision segmentation pipeline from last time. We already have our pipeline for most of these steps, so in this lecture, we will be mostly focusing on these two, feature extraction and segmentation. Feature extraction, for us, are a series of techniques to extract or obtain information from the input image. These features can be obtained using image processing, computer vision, and/or a variety of other methods such as statistics. Examples of features that you can extract from an image include pixel intensity values, edges, corners, and others such as blobs and circles. Since our particular image has a lot of edges and corners and not many blobs or circles, we will mostly be focusing on the first 3 examples. Back with the code. If you've been following along with me, you should have a project set up similar to this, where you've got Lecture 1 and Lecture 2, IPY and B. For this lecture, we will be working off of Lecture 2, so let's duplicate this and rename it. to lecture 3. Now let's open it and have the kernel restart and run all so that your input data is in the cache. Give it a minute. Looks good. So when doing feature extraction, you can extract features from the preprocessed image, or you could also work directly from the original image. For this module, I will be working off of the original image because I'm a heathen. Hopefully you can see this. So let's rename this feature extraction. And we mentioned before that we want to extract 3 features: intensity, edges, and corners. So for the intensity, the original image is very noisy. So let's see if we can get some sort of filter. You could use the mean filter as last time. I'm going to be using Gaussian. So intensity equals skimage.filters.Gaussian. And then pass in the original image. What did we name it? Oh, original image. That's helpful. And then let's show it using our custom IamShow. And name it Gaussian blur. Hopefully this runs. It does look sufficiently blurred. It's a little bit hard to see, so I'm actually going to zoom in by slicing. So 0, 100, 0, 100. Run again. Yes, it is definitely blurred. So that's feature 1. Feature 2, we want edges. And for edges, I'm going to be using Farid edges. So I think it's skimage.filters.Farid. And then the input, I think, is just the original image. And I'm a little bit lazy, so I'm going to copy paste the IamShow again. And name this edges. And these are Farid edges. Run the code. So Gaussian blur is showing Farid edges. As you can see, there's a strong response or a light color where there are strong edges. There's also a lot of light color wherever there's a lot of noise. But overall, we're pretty satisfied with what we're seeing, so we're going to keep it. Next, we want corners. So this is going to be skimage.filters. No, it's feature. I can spell. And then corner. There's a couple different ways to extract corners. I'm going to use Harris, but you can use others. So original image. And then we want to show this. So corners. And these are Harris corners. Hopefully this runs. Gaussian blur, Farid edges, and Harris corners. So as you can see, there's a very strong response where there are corners in the image. Again, there's a little bit of noise in the initial image, so there's going to be noise in the edge and corner responses. But overall, we're pretty happy. Now let's format this. So to format the features, we need to make it into a stack. So let's name it features equals numpy.d stack. And I think it needs to be a list. So you got intensity, corners, and edges. Oh, edges and then corners. The ordering does matter for later on when we do the explainability methods. And then features. So we want to reshape this so that way it's features dot reshape. And we want to do all of these images they should be 800 by 800, same as the original image. So let's try that. 800 times 800. And then -1 is whatever shape it needs to be to make sure that the first shape value is going to be whatever 800 times 800 is going to be. If we want to see what that shape is, I can print it off. Print features.shape. Let's run that off. So we have it. The features are now 800 times 800 by 3. This is the proper format. Doesn't matter. If you want to add additional features, you can. No matter what you add, it should be this number, and this number should be however many features that you've got. We will be doing segmentation using an unsupervised machine learning method in the next video. K-means clustering is an unsupervised machine learning technique that can be used for image segmentation. It operates by iteratively grouping data based on inter-cluster variance of the extracted features. It requires 2 inputs, the number of clusters, so in our case, 2, because we only have background and foreground, and input features. To illustrate its operation, we have prepared the following example. Suppose we extracted only 2 features. So for example, feature 1 could be intensity, and feature 2 could be edges. And then we plot each pixel based on these 2 features. At iteration 0, so the initial condition, we randomly pick 2 points in space to be the initial cluster centers. Now, all points closest to cluster center 1 are grouped into cluster 1, and all points closest to cluster center 2 are grouped into cluster 2. In the next iteration, we move to the cluster centers based on the centroids of the current clusters. And then we update the clusters based on that new update. This process repeats until the cluster centers are stable. In this toy example, we basically have a grouping that most people would probably consider is correct within just 1 iteration, but some scenarios may take more than 1 iteration, especially if the initial centers were not very good. Since the final result depends so much on the initial cluster centers, it can be helpful to play around with a few different initializations and pick the most common final solution. If you are interested in learning more about k-means clustering, please refer to Hartigan and Wong's paper entitled A K-means Clustering Algorithm, linked in the description. Now that we went over k-means clustering, let's start applying this to our project. Building off our work from last time, we have now extracted some features. Now we want to segment using unsupervised machine learning based on these features. So let's update this block. This is no longer applicable, so we're gonna delete the Atsu thresholding block and start anew. So we're going to be using unsupervised machine learning and k-means. So for this, we need to import clustering. Let's move this up so you can see it. Import sklearn.cluster. And we want to initialize our model. So model equals sklearn.cluster dot k-means and clusters equals 2. 2 because you got foreground versus background. Random state. You don't have to do this, but it's a good idea to put a random state. This is just going to determine where the initialized parameters are going to go, or those initial cluster centers. When playing around, it's really difficult when your outputs are changing so much. So I like to set a random state. So model.fit. Now let's actually fit the model based on the features. And now let's actually predict. So let's name this clustered image. So this is going to be model.predict features. This is going to be a weird shape, so we want to reshape this to be the original shape. So clustered image dot reshape, and the original image size was 800 by 800. And we want to show this. IMShow clustered image, and name it clustered image. Hopefully this runs. So it is running. You'll notice that the foreground is completely different from the background, whereas we want the foreground to be white and the background to be black, but it is flipped. So you can play around with the random state again. I mentioned it before. So 0 didn't work. Let's try another one. Let's try 1. That also didn't work. Play around with it until you find something that works. I think I tried 12 last time. This looks good. So now it is flipped properly, where the foreground is now bright and the background is now dark. Now that we have named this clustered image, in order to not break our code for post-processing, we actually need to rename this so the input is no longer a thresholded image, it is now a clustered image. So now every place that you see thresholded image, you should replace it with clustered image. So that's not there, not there. Thresholded image needs to be put clustered image, and we're good. So to see the result, let's run this. And then let's see the impact it has on the IOU score by running everything below. So before we had 0.884. Let's see if this did anything. 0.83. It went a little bit down. Visualize the results. Okay, so it went a little bit down, but that's okay. You can play around with k-means. Maybe it would be better to extract features from the preprocessed image. I'll let you do that in your project. Sometimes, as part of the evaluation or deployment process, we want to take a look into the internals of our algorithm. If the algorithm is performing well, we might want to know why, so we can just ensure it is indeed working how we want it to, or maybe there are some new insights to be gained that we weren't expecting. If the algorithm is performing poorly, it is also important to know why, so that we can fix it. Explainable AI, or XAI for short, is a set of techniques to make AI algorithms interpretable by humans. For k-means clustering, one way we can interpret the results is by viewing the cluster centers and where they ultimately end up. To see what we mean, let's start applying this to our project. Now that we've got our results and find that the performance is pretty okay, let's actually break this apart and start explaining it. So we want to do this after visualizing the results, so insert a cell below. And we can call this model interpretation. And this is going to be using the cluster centers. So if you look up the documentation in sklearn, k-means has this nice property where it has cluster centers that it gives to you. So for us, I'm going to move this up so that you can see a little better. Let's just add a couple cells below so that you can see. For label model dot cluster center and enumerate model dot cluster centers plural, we want to print off the label I think we can do this. This is just making the print pretty. Model dot cluster center. Now we run. Hopefully it runs. Alright, so for label 0 and label 1, these are the centers of the centroids for each cluster. So as a reminder, label 0 or false is going to be where the dark is. Label 1 is where the bright is, or that's the foreground. So I mentioned before that we do care about the ordering of these. So let's just go back and look at our features real fast. And notice that we took intensity, then edges, then corners. I'm going to copy that so that we don't forget it and go back down. So just gonna comment that. So how do we read this? This is telling me that in general, the foreground has a lighter intensity or a higher intensity than the background. That checks out. We've been talking about this for a while now. This also tells us that the foreground, the edges are a little bit higher in the foreground than in the background. Same thing for the corners. There's really not... Oop. Autosave is moving this too much. Sorry about that. This is also telling us that corners for label 1 or the foreground, there are more or a higher response in the corner image than in the background. And you can use this to explain your results when you are training your model. There are a number of extensions that could possibly improve your project. For feature extraction, we used blurring, edge detection, and corner detection. You can always play around with the parameters for the methods we already used, or consider using other methods, such as rectangle detection. skimage has a variety of filters and features that you can use, and if you just want to play around with a bunch of features and see what works and what doesn't, you might want to consider using a feature selection method, such as linear discriminant analysis, or LDA for short. If you end up using a bunch of features with widely different ranges, you might want to consider using a feature normalization technique, such as standard scalar. For segmentation, we used k-means clustering, but there are a variety of other clustering methods that you could use, such as spectral clustering and bisecting k-means. The explainability methods may differ for different algorithms, so you may need to search for other approaches. As always, we encourage you to experiment, see the effects for yourself, and maybe try out some methods that are not listed on this slide. For some inspiration, please refer to the skimage and sklearn library documentations linked in the description. In summary, this is what we covered today. We introduced the concept of machine learning, some of the different types, and focus on unsupervised learning. We applied blurring, edge detection, and corner detection as a feature extraction techniques. We applied k-means clustering as an unsupervised learning segmentation technique. We introduced the concept of explainable AI and used cluster centers to understand our k-means clustering algorithm. and we suggested a few potential extensions for you to look into and experiment. In the next video, I'll be expanding our work here using a supervised machine learning approach. Thank you for your time.